Virginia is one of the co-spokespeople of the DUNE collaboration. And I'm sure she'll probably tell you it's a very large collaboration, international, from scientists from all over the world. And she and Josh Wilhite and Jolie Messier, who are part of the project building this experiment, are underground, and they're going to explain to you some of the details of what's happening. So, Virginia, over to you.
Hi, everybody. Can you hear me?
We need the
we can.
Yeah. Okay. All right. Well,
just a second.
Oh.
Is your mic on? And is it? We're getting it very faintly.
My mic is on.
Yeah, it should be. There must be some audio problem at the Opera House because Jolie can hear us.
Josh's mic is very loud. Josh's mic is fine.
Can you hear me?
Steve.
So down in my mic.
Yeah, can you switch mics?
Yep. I can.
Okay.
Sorry,
folks. Technical difficulties of communicating with a mile underground.
Is this better?
Sure. We'll
Okay, very good. Hi, everybody. I think Jared was asking, for whom this is the first Neutrino Day. I don't know if you saw me, but I raised my hand. This is my first time also being at Neutrino Day, so I'm very excited. And you can see right now, I'm standing in the caverns in my Ontario, where the DUNE experiment
Can you hold on a second? We're still having trouble with sound levels.
You still can't hear me?
We can hear you, but very faintly.
Maybe I should switch to your microphone.
All right, can you hear me, Steve?
No. So, Jim, if you hold it like that, that works just fine.
Okay.
Okay, I see. All right. So, did you hear me so far? Or...
Yeah, we can hear you fine. If you hold it up maybe an inch closer, you should go.
Okay. All right, I'll do that. Well, technical difficulties in mine under here. So, all right. So I was going to give a quick overview of DUNE. The DUNE experiment stands for the Deep Underground Neutrino Experiment, I mentioned before. And the apparatus of the experiment spans a large fraction of the Earth. And this is typical of neutrino experiments. Some of you may know already. So the neutrinos for the DUNE experiment come from Fermilab. And this beam would be the highest intensity neutrino beam we'll ever produce. When I say intensity, I mean, in layperson terms, that means most particle-packed beam. And the more neutrinos we can pack in there, the better. And we sent that beam from Fermilab to South Dakota to lead to the Sanford Underground facility, where we are right now. And neutrinos will travel about 800 miles to get here. Yeah, that's the longest distance neutrinos have ever traveled from an accelerator. And before they make their travel to South Dakota, we will have a near detector, what we call a near detector, because it's sitting closer to the beam at Fermilab. And this detector will sample the neutrinos for their energy, for their flavor, how many types of neutrinos, and we record that, and then we let neutrinos travel 800 miles. And as several of you may know, neutrinos have this morphing nature where they tend to change types and out long distances. And then we record that spectra with gigantic detectors that will move in these caverns, sir. So that's basically how the experiment is laid out. And let me talk a little bit about the far side. Like I mentioned, I'm right now standing at the center of these two caverns. And these are colossal caverns. You can see that in other views, cathedral-like caverns. And that speaks to how big the detectors are going to be. So these will be the largest detectors of their kind. So these are liquid argon detectors. So we fill the cryostat, the refrigerator that holds the detector with liquid argon. And to put the dimensions in perspective, you're looking at a 7-story high a detector module, or the length is of this called stadium, for example. So they're the largest of their kind. You probably noticed as I was describing DUNE, it's hard to describe DUNE without using superlatives. That tells you how unprecedented both the scale of the detector is. And that gets me to the science. The science will also be unprecedented that DUNE will do. One of the main questions that DUNE is after, and using neutrinos and do the measurement in the best possible way, is to understand the very basic question of why do we live in a matter domain. We go to Big Bang, the expectation is matter and antimatter form in equal quantities. It's like plus and minus, matter and antimatter. So you expect them to cancel, and then they would just be light. And the fact that, we are here today tells you that something happened at the beginning of the universe that made matter survive than antimatter. And the neutrinos being at the center of this mystery. So this is a question that DUNE will explore as a primary goal. And the experiment is designed in terms of where we located the detectors, the beam, the type of the technology, is all designed to maximize our sensitivity to answer this question. The other question DUNE will answer is also the mass order, is what we call the mass ordering of neutrinos. Although we've been studying neutrinos for almost a century, there's many things we don't know. And one of the questions is which neutrino is the heaviest, or which one is the lightest. So DUNE will shed light on the question of mass ordering. And there's lots of other cool slides that DUNE will do. For example, whenever something, explosive happens in the cosmos, whether it be black holes, neutron stars, or stars forming or exploding, which we call supernovae, you get a ton of neutrinos that get produced. And since neutrinos are not very sociable, you have to really, go above and beyond to make them interact in our detectors. But they come in huge quantities, and DUNE, given its size, will be able to record those neutrinos. So we can study how the sun works. We can study what happened when a star exploded, when supernova happened. And then DUNE, just by the design, is also very sensitive to new exotic physics. Physics that we don't know may exist. Think about dark neutrinos. Is there a fourth type of neutrino? So those are the science goals of DUNE. I'll briefly comment on the collaboration. Building an experiment at this scale, it's hard to be done by one person or even 100 people. So our collaboration is more than 1,500 people, and that spans 38 countries and more than 200 institutes. And this is worldwide. So DUNE is a truly global endeavor in order to bring this unprecedented vision to reality. We have collaborators coming from, many corners of the world. We have folks from India, South Korea, we have folks from Madagascar, we have folks from United Kingdom, Switzerland, Latin America, Brazil, smaller countries in Europe like Armenia, you name it. The world is really coming together to make this vision a reality. I'll quickly end before I get to Josh. I'll mention that the experiment, the collaboration, we are at a very exciting phase right now. You're noticing in the other view, you can see that's red structures behind me. That's the materials of the first detector component we built, which is this refrigerator, what we refer to as cryostat, that holds the detector and keep argon. So we're really starting that installation in a couple of months, and we're very excited for it. The collaboration will start coming here from all corners of the world in order to build this detector, and we'll start taking data in early 2030. So very exciting times. And with that, I'll pass this on to Josh, who will tell you more on what's going on here.
All right. Thank you, Sojonia. Can you hear me in the room okay? Have to get the camera to follow me instead of...
Yeah, we can hear you just one.
We'll get there. All right. I got to get it on my face here. Hold on a second. Maybe. There, it's following me. All right, so I'm Josh Wilhite. I am the project manager that's been responsible for the excavation and what we call the Building and Site Infrastructure, or BSI, in support of the LBNF DUNE project. And so I just want to point out behind me here while I'm standing and thinking about it, So John, you talked about our collaboration, and this beam behind me, it might be a little hard to see, but that actually has the signatures of all the collaborators. Many of you may have been involved in the beam signing that happened at the visitor center. Unfortunately, we put a couple beams in front of it, but it is actually right underneath that one that you can see with the signatures. And so, yes, your signature is a mile underground now, and it will be prominently at the top of the detector once we're done building the detectors. So just wanted to give you a little background of how we got to where we're at right now. Obviously, these caverns that we're standing in now didn't exist when I started with the project. And so we actually had to restore many of the systems that were here for mining back in the homestake days, including the skipping system that brought the rock to the surface. And then we installed that conveyor that goes across the road as you come into town. Everybody probably drove under it. If you didn't notice it, you'll drive under it when you leave Lead, if you don't go through Central City. And so that allowed us to excavate underground and deliver about 800,000 tons of rock into the open cut using that conveyor belt. And so as you go to the visitor center and actually just up the street from the visitor center, there's a good viewpoint. You can see how little of a impact 800,000 tons of rock makes on that gigantic open cut in Lead, South Dakota. And so we started doing that work in 2019, perfect time to do a construction project right through a pandemic. But we were successfully able to do that with no lost time injuries. And so that's something we're very proud of. And in fact, the excavation part of the project, just recently, I went to California and was happy to be able to receive the Project of the Year award from the Underground Construction Association. And so these are, as Sojanya described, these are the largest caverns in the world at depth. And so we built these caverns 65 feet wide, 92 feet tall, and 475 feet long. Two detector caverns of that size. They're a little bit longer when you get to the top. And then we've got a central utility cavern that's actually the same width. It's only about 35 feet tall, but it's 625 feet long. And so very, very long cavern. Very, we got a little noise in the background here. I hope that's not disturbing the audio, but very impressive caverns. I wish we could bring everybody down here because it's pretty hard to describe just how impressive these caverns are. Yeah, so I think they just flipped up the picture of the cavern. We're just out of frame on the bottom of that picture. We tried to get Zach to move it, but he wouldn't move it any further. So you can't quite see us. Jolie's actually going to walk around the end there so you can see kind of where we're at in the frame. So we built these big caverns. What's the next step? Well, we got to put in the infrastructure. And so putting in the infrastructure means effectively the same thing you do with any building. Just so happens we're a mile underground. And so we have to put in lights. We have to put in the fire protection system, the fire detection systems. We have to distribute power around the level. We've got to put in cooling systems. A couple of unique things about what I just described. So power, I'll start with the power. We're using about 7 megawatts of power to power this experiment, which is a huge number. City the size of Lead, someday I'll look this up, but a city the size of Lead, typically you're going to use 2 to 3 megawatts. And so we're using, 2 to 3 times as much power for these experiments than a city would need. Most of that power is actually used to make the argon liquid. Argon isn't liquid unless it's negative 300 degrees Fahrenheit. And so you have to cool it down to that temperature in some way. And so the way we do that is we actually install a nitrogen generator and liquid nitrogen compressors. So that means we extract nitrogen out of the air. That's most of what you're breathing right now is nitrogen. And then we put it through turbo expanders, which are kind of like jet engines in reverse. It expands that very, very, very much, and that actually cools it down, just like if you're blowing compressed air on your computer and the tip of that nozzle gets an ice ball on it. That's exactly the same process we're doing. And so we cool it down into a liquid form, and then we can fill the detectors. Now, by doing that, by creating that liquid argon, we actually generate a lot of heat. We're effectively extracting the heat out of the argon, and we got to get rid of that heat somehow. And so on the surface, your air conditioner at home just blows the heat outside, right? If you stand next to that fan-looking condenser outside your house, it's blowing hot air. Well, that's what it's doing. It's removing the heat from the house and taking it outside. Well, outside to us is a mile up. And so we do effectively the same thing. We've got chillers that are called, and we've got condensed water that goes to a cooling tower. And at the end of that cooling tower, we actually built one of the largest and longest boreholes ever done on Earth, about 1,200 feet vertically and 12 feet in diameter. And that connects us to an existing shaft, the Oro Hondo shaft in Kurt Canyon, that then pulls that air out from the underground. And that air was very critical to us during excavation because we get a lot of diesel equipment operating, and so we got to get rid of that diesel exhaust. And it's very critical to us during operation because of that heat. So we circulate water, and then the water is cooled off by air flowing through that cooling tower and then up that borehole. And so you're probably familiar, if you've ever been in Kurt Canyon, there's already steam, looks like steam. It's not steam, it's condensation coming out of that fan. And that's exactly what we're doing. We're cooling off the underground and we're taking it to the surface. So that's a pretty unique thing, working a mile underground. We can't just blow the heat into the air like you do on the surface. And so we've been working pretty hard over the last couple of years, getting things in place to the point where this steel that's behind me and in the big picture is now ready to be assembled underground. And so we're not done with the BSI project yet, but we're done enough to allow the experiment to happen. And then I'll talk about one other thing before I turn it over to Jolie, and that is that when you think about working a mile underground and you think about excavating the world's largest caverns, and in fact you think about putting in electrical transformers underground or gigantic beams, you have to really plan for how you're going to move that stuff through the shaft. The only way to get to where I'm at is through either the Ross shaft or the Yates shaft. And those shafts are effectively the same size. About 5 foot wide and about 12 feet long is the size of the cage or the elevator car that brings us down. Now we can go a lot longer in the vertical, but that 5 feet by 12 feet, that's all you get. And so we brought down some of the largest excavation equipment in the world to do the excavation. And we did that by cutting it up into pieces, bringing it underground, and putting it all back together. Just like the FAR detectors are being taken apart into pieces like that you see behind me, brought underground, and then they'll be put back together. And so that's really something we have to think about all the time with everything we do underground. So with that, I'm going to turn it over to Jolie. I think she's going to be standing in the middle of the cavern in the big picture. Go ahead, Jolie.
Okay, so we've talked about these pieces of steel. For each of the detectors, we need 1,326 pieces of steel to be brought underground. And we are in that process right now. So, and I know we alluded to some sounds of equipment that you may hear. I don't think you do, but if you do, that's our team moving other pieces of steel around to be able to start the installation of those very large cryostats. So the cryostats themselves, these pieces, the design of these, the manufacturing of these, the shipment of these. So yes, as I said, we're in the process of getting the steel underground. Right now, it's in Rapid City. The steel for 2 cryostats is in Rapid City. And we are in the process of trucking it up. So those of you who are local, you may see the trucks going by, semi-trucks going by with steel on them. In fact, yesterday I saw at least, when I was in the right spot, I saw 2 trucks go by. I think 3 or 4 went by. And it's very exciting to get it into the shaft and underground. So our teams, as I mentioned, are working to get underground. Then we are working with CERN to do the installation. They have hired a company from Minnesota who will do the installation, and they will begin that later this year. So very appreciative for this partnership, and this really speaks to the international aspects of DUNE and the compelling science that is to be wrought from this experiment. So for the moment, Steve, any questions from the crowd?
I think before we turn to Q&A, I think the project director of this whole exercise, well, he's in his spare time as project director, and for now he's a distributor of merch as an announcement.
This is actually the most fun you get to have as a project director. Anyway, my name is Jim Kirby. I'm the project director for LPN DUNE as a whole, and slightly winging it here is to mention a couple things that will start at 11 but go on the rest of the day. And so if you don't happen to stay for the whole underground, we'll make this announcement at the end as well. So aside from learning a bit about neutrinos and what's driving down the streets here and what's going on in the town, everybody, as far as I can tell, really needs a small baby bison hover. Okay, and so every hour starting at 11 a.m. over at the visitor center, there will be one of these given away. There's a trivia contest you have to enter. I assume it's not too hard, but you ought to be able to figure it out. And if you have, children, a spouse, I'm pretty sure my wife of 33 years would be quite surprised to get one of these. So, surprise somebody you love with one. And there's 5 total. And once they're gone, they're gone. But if you visit us in Batavia, Illinois, there's something there too. Also, Josh, there you go. Perfect timing. There are 2 baby bison and mama bison plushies, and they are underground. There are very few things that go underground aside from piles of steel and things like that. These will also be given away. There will be a drawing at noon and another at 2:30 at the Fermilab booth in the visitor center. Under my chin, there we go. Sorry about that. These will be drawn at noon and 2:30 at the Fermilab booth at the visitor center. They come with a certificate of authenticity. So just in case you're worried that they weren't underground, it's those 2. So Ginny and Josh, you look great with those, but we're going to rip them out of your hands later. And they'll be given away to everybody. Okay, so you have to participate in the trivia contest. Don't get too emotionally attached to them, you guys. And but we're very glad you're here. I'm out here a lot, as our whole team, and we look forward to this being the center of underground science for decades to come. So thank you very much. Get a hugger and get a baby bison.
Right, thanks, Jim. So we have the opportunity now for some Q&A with our folks underground. I think Jarrett and I are going to come down and less in the clouds. So you heard from Sujini Golopini first, who's one of the co-spokespeople of the DUNE collaboration, leading the scientists, and then from Josh Wilhite, who heads the BSI sub-project, and then from Johnny Macia, who's in charge of building these detectors. So yeah, if we've got questions.
What is it about argon that makes it so critical to these detectors?
I'm going to throw the one to Virginia.
Yeah, I think I heard that. What is it about argon that makes it critical for the experiment? Did I get that right?
Yes.
Okay, great. So argon is what we call a noble element. There are other noble elements, xenon, for example, helium. Those you may have heard. We have some work going on, so there is some background noise. Okay, that has gone down. So noble elements in general are really good, in terms of providing a medium for particles to interact. You can get most signal out of them. They tend to drift signals light in a way where it's maximized. So that's one of the reasons many of our experiments use these noble elements. With liquid argon in particular, there's many other benefits. One is, it's transparent to the light that are produced by neutrinos. So you detect almost all the light that's produced.
and they propagate nicely in the detector. In terms of charge as well, the way the liquid argon detectors work is you have a neutrino coming in, interacting with an argon atom, and then that produces charged particles, which then ionize argon. Ionization is basically stripping electrons off of atoms. As you know, atom has a nucleus and then electrons orbiting around. So you strip those electrons off, and those are your signal. We call them the ionization electrons. So argon is a really good medium where you get in the amount of ionization electrons you get is really great. So those are two reasons. One of the other reasons is if we can do this experiment with xenon, we could, but I don't think there is enough xenon in the world to fill our 70,000 tons of detectors. So argon was that really nice balance of giving the properties we need. Also in terms of cost, xenon is probably $1,000 per a few liters or so. Argon is a few dollars per liter, although the price has gone up recently. So a combination of all those things is why we went with liquid argon.
Yes. My question is, why does the detector have to be so far from where the beam is generated? Why can't you either have the beam here and next to the detector, or the detector next to where the beam is generated?
Great question. So this is, typically the design of the long baseline experiments. For the science we want to extract, you want neutrinos to travel a reasonable distance, hundreds of kilometers. What that exact number is depends on each experiment's specific goals. So in a long baseline experiment, which is what DUNE is, you put the two detectors. One is a detector, what we call the near detector, that sits closest to the beam. So in the case of DUNE, at Fermilab, we'll have a smaller detector that will sit about half a kilometer from the beam. And then the neutrinos travel 800 miles, and then and then we have the far detector here at SURF. So that distance is important because you want neutrinos to oscillate. And in the case of oscillation of neutrinos, that's a jargony term. It's another way to say, neutrinos are weird particles. Good weird, I would say, because that weirdness is really what makes them great probes to extract the science we want. So neutrinos, when they travel long distances, they have the tendency to morph into different types. If you start with an electron neutrino at the far detector, hundreds of miles away, you may not see an electron neutrino. It may have morphed into a muon neutrino, and that's what you measured. This phenomena of morphing or the oscillations is really at the core of the science that we do. So from that definition, the detector needs to be far away. So you sample the neutrinos before they morph, and then you sample the neutrinos after they morph, and you compare those two things. And that's what makes you sensitive to the science goals that we talked about just before. In the case of DUNE, one additional factor is we want the neutrinos to oscillate in matter. So they're not passing through the air. They're not passing through on the surface of the Earth, right? They're actually probing into the Earth. And when neutrinos oscillate in matter, that also brings in, the sensitivity, whether it be mass ordering of neutrinos or the matter-antimatter asymmetry. The neutrinos tend to behave differently in matter. So, and that's another requirement for us to be able to extract the science, whether with the understanding the mass ordering of the neutrinos. So that's primarily the reason why one detector tends to be far, and we carefully choose that distance. Not that there's many underground labs like this we can build. As Josh mentioned, these are the largest caverns. So, there is some understanding of how long the neutrinos can travel, where the far site could be. And I think we landed greatly in the sense, with Fermilab as the near site and then the SURF as the far site.
Question here?
I just had a question, trying to envision with all the beams and the structure that you're building, like, are they bolted together? How close are they? And what holds the liquid in? Is there like some type of a bladder, or is it just the beams, or however that's working?
Yeah, great question. So yes, the steel will be bolted together, and then there'll be an internal steel layer. And then we'll put about a 3-foot thick set of insulation. So essentially that's what makes the cooler. And then we'll install the detector elements, and then we'll fill it with the liquid argon. Sorry.
Hi, I'm Tom Lewis. This question is probably mostly for Josh. 6 years ago, I worked with Kiewit, helped rehab the tramway tunnel, and then we mucked out, bolted the 4850 bypass, overpass, and then we helped build the grizzly deck over top of the dump. My question is, how did you guys actually cut the 60-foot wedge out from the Ross station so you got room for your steel? Because nobody ever gave us that answer when we asked.
Carefully, is that a good answer? So no, the way that we cut the excavated the brow area, which is what's being described there, right next to the shaft, we started the furthest away from the shaft, and we drilled up perimeter holes and then brought those down. And then when we got close to the shaft, we actually built a barrier against the shaft steel. And then the last, I want to say it was 4 or 5 feet of rock was, I would say, very delicately excavated out. Most of it just the deck cord itself to break that rock and bring it down safely. And of course, they were bolting as they were approaching to make sure that they were safe. And they were using the rock that was coming down to build a ramp to get them access to drill further up. Does that answer the question?
The steep ramp. Yes, thank you. You couldn't do that in Nevada, I want to tell you. The rock would not hold together.
So my question is the purpose of DUNE, are you trying to measure the mass of neutrinos at all? Because I know that is a question that is being tried to answer.
I think I heard the first part of the question, if we're trying to measure the mass, and I didn't hear the second part of the question.
Yeah, and you got the question.
Yeah, that's okay. Yeah, so we are making a mass measurement in the sense that it's not the absolute mass of neutrinos. So we're not, long baseline experiments like DUNE by design cannot measure, okay, neutrino weighs this much, or, so I think what we're trying to measure is what we call the mass square difference. This goes a little bit into the mathematical framework of neutrinos, but based on those mass square differences, which is what these type of experiments are sensitive to, you can arrange the mass states of neutrinos in certain ordering. There are 3 mass square differences and 2 mass splittings is what we say. And one of the mass splitting, we know the ordering there because we use the neutrinos from the sun to measure that. And since neutrinos go through the core of the sun, they're going through matter. So then you're sensitive to that mass ordering. So it relates to my previous point as to why it's really important for DUNE that neutrinos go through matter, the earth, rather than just in air or vacuum. So with DUNE, we will be sensitive to the second mass ordering, which is a big open question right now, because, without knowing the sign of that, you can arrange the neutrino mass order, the squared masses, in 2 ways. What we call the normal hierarchy, that's one way of arrangement, and then the inverted hierarchy. So with DUNE, we'll be able to definitively measure what that which of those ordering, inverted or normal, is correct. And the emphasis of neutrinos going through matter again comes from the fact that you have several overlapping effects, and you need in addition to going through matter, you need a very long baseline, and DUNE gives that 800 miles neutrinos travel. You can also separate these overlapping effects, because the matter antimatter effect also comes through. Then there is the mass ordering effect that comes through. But again, with the very long baseline, you can separate those two. So DUNE can actually make very clean measurement compared to any other experiment in the world when it comes to this mass ordering. Hopefully that addressed your question.
We have a question here. And before we move on to that, I just want to emphasize or highlight the premise of that question. Our theorists invented the neutrino in the 1930s. We're now celebrating 70 years since the discovery of the neutrino. So we've had 70 years to study this particle, and we still don't know how much it weighs, which speaks to how mysterious, how hard it is to study this particular particle. We think that the universe has a number of secrets tied up in how the neutrino interacts with nature, and that's what we're probing here. But that was a great question, and it really does highlight how special this particle is. Question here in the front.
Yes, I have a question about the cavern you're in. I noticed you have several what appears to be white lights along the sides of the cavern, and I was wondering what the functionality of that is, because I imagine stability is very important.
Here's the question. So the question about the lights, correct?
Yeah, question about the lights and then stability overall.
Yeah, okay. I'll take the question of the lights, and then I'll defer to Joshua for the second part of that. So yeah, the lights are merely to provide a good working environment for our team. Obviously, during the era of excavation, where we had temporary lighting and so forth, we relied also on our camp lamps underground. But as we prepare to fully execute installation activities in this space and transition from a fully construction phase, we added the lights.
So what was the second part of the question?
But the stability.
The rock stability, is that the question?
Yeah, maybe a comment on rock stability.
Yeah, so we're very fortunate. This is one of the reasons why this site was selected. So Janya described that it's a sweet spot distance away from Fermilab, but it's also very, very competent rock. And so some other facilities through the DOE complex and other mines, of course, you get a lot of ground movement after you excavate. This facility, we did get ground movement immediately upon excavation, up to a couple of inches in some areas because these caverns are so large. But beyond that initial movement, it settles down very quickly. And so the long-term stability of these caverns, we expect something on the order of a few millimeters of additional movement over the life of the experiment, which is, on the order of 30 years. So very, very stable caverns. It's excellent rock. Another thing I didn't mention that makes this site very nice, not that we couldn't have handled water, but there is no water dripping in these caverns. This is a very dry underground space. There's a lot of mines where you get a lot of water flowing in, and there are other underground labs that have to deal with a lot of water coming in just because, hey, we're a mile underground. We're below the water table for sure. But in this particular case, part of the reason we don't have water is the rock is so competent. So for example, when the Homestake mine shut down and stopped the pumps, it actually flooded 300 feet above this level, the 4850 level. Despite that, when we were able to dewater and get back into the underground, there were air pockets where the rock was so solid the air couldn't get through it to allow water to get into there. And so this is very, very competent rock, very stable underground environment.
Other questions?
I may have missed something because I didn't hear right at the very beginning, but a few years ago, when I visited Neutrino Days, if I understand this right, there was going to be a beam that was going to travel from a Chicago lab to here. And so I'm wondering what the progress is on beams traveling to and from this lab.
Did you catch that?
So we have some noise.
Versus the cryostat beam. So the question about the beam line traveling from
Fermilab to
Illinois
is the question about readiness or is the question
just general?
I see. Yeah. Yeah, so as we mentioned before, we'll have the highest intensity beam, a megawatt scale that will come from Fermilab to here in South Dakota. And the way the whole beam line is designed is neutrinos, once you shoot neutrinos in one direction, that's it. They keep going. There is no changing their direction or, you can't do anything. So the way the beam line is designed is it shoots neutrinos through the earth, pointing to the caverns in South Dakota. And there's a lot of, very detailed planning that went into it, design and planning and engineering. So that way we see the most of the beam in our far detectors. The beauty of neutrinos is that you don't need a beam line for it. They, like I was saying before, they're not very sociable. In fact, we have to come with all of our tricks in the bag to make them interact in our detectors. So once you shoot them down in the direction of surf where the dune caverns will be, they just keep going. And then we minimally lose them. I would say almost all of the flux comes through, and we look at those interactions in the detector. So the work to get the beam line. So in order to, right now, the capability of Fermilab is a kilowatt beam, just to give you a reference. So we need to go from there to a megawatt beam, and that requires a series of upgrades in the Fermilab accelerator complex. A new LINAC, a linear accelerator that can get the protons to higher energies, and then they go through these circular rings, what we call boosters, that gets us to the megawatt scale intensity that we need. And that work is ongoing, and we anticipate first megawatt scale beam to dune in 2031. I hope that answered the question.
Describing how beams got here. Physical beams.
These beams.
Yeah, so just to make life even more confusing, we refer to these steel pieces quite often as beams. And so these elements that will form a full rectangle, 6 stories high, all have traveled from their manufacturing location in Spain. And so over time, those got shipped from Spain on a boat, and then by truck to Rapid City. And then, as I said, by truck again from Rapid City to here. And then they get loaded into the shaft and then move downward. And then we assemble them here.
Josh, can you hear me?
Yeah, I got to get closer, but yeah, go ahead.
Okay. Yes, there are questions here. I worked in Nevada for several years in the nuclear testing program. We did a lot of shaft work, a lot of tunnel work. And my question is, how much problem did you have drilling through this rock? What type of rock is it? And what size drilling machines did you actually use to get where you're at?
Yeah, so we use twin boom jumbos. I can't remember right now just exactly what the model was. It is very hard rock, but with those twin boom jumbos, of course, it'd take I think it was about 30 seconds per hole to actually drill the 15 feet. They handled it very well. It's a schist is what we're in here. And so it's very competent, as we said. It does have a lot of foliation in it, And so something that we have to pay attention to if you're not using a jumbo that's pretty rigid is if you're using jack legs, for example, the bits do tend to veer off a little bit because it'll hit that foliation and try to turn. So something kind of related to that we had to deal with was this borehole I described, the 1,200 vertical feet from the 3650 level down to the 4850 level. That was something we were very worried about, was being able to actually hit the target at the bottom. And so we got a steerable, if you will. It was kind of built in, had inclinometers in it, and we were able to actually hit our target within 6 inches when we got to the bottom. So we were pretty excited the day that broke through. I think I hit all the questions there.
Okay, thanks, Josh. Any other questions? Yeah.
I know that Fermilab worked for a long time with the underground mine physics lab at Sudan in northern Minnesota. Were the experiments that they did in that lab, are they still ongoing? And what have you guys learned from those?
Yeah, the other longer baseline experiments from Fermilab, I guess I didn't hear the question fully. I guess you're referring to the NOVA experiment. Yes, that experiment's still ongoing. And very much so. They have, several years ago, they have finished construction. They also have this near and far detector. They have been taking data. In fact, they're putting out interesting measurements. Like DUNE, it's also a long baseline experiment. So they're also looking at similar science goals. The matter antimatter question, the mass ordering question. Their sensitivity is limited because the baseline of that experiment is shorter than DUNE. And then, there are other factors as detector capabilities and so on, but they have been consistently shedding light on when it comes to the question of mass ordering. NOAA has the ability to go up to 3 sigma or so, if they can get their uncertainties and everything under control, in terms of sensitivity for the mass ordering. But analysis is going very well. In fact, there are other experiments that have started recently. Juno is another experiment. So NOAA and Juno has tried to do combined analysis, which is something we do in our field. When you have data from multiple long baseline experiments, you can do global analysis of the data, and that helps maximize sensitivity in some cases. So all those efforts are very much ongoing.
Back in the Sudan mine itself, there was an earlier experiment, MIMOS, you're referring to, which we decommissioned a few years ago. And the NOVA experiment that Virginia is referring to, we will decommission that in order to build the beam line that she was talking about earlier to lead South Dakota. So there's a progression of, you learn something, you do an experiment that helps to inform the next experiment that you do, and so on. And the MIMOS experiment in Sudan was definitely an important part of that progression. Other questions?
Hi, Josh. This is Tom Lewis again. I was fortunate enough to be able to help bolt a borehole chamber on the 3650 after it was cut out. And I'm just curious how you got your big borehole equipment across the 3650, because I know the scale of the equipment we were using when we were bucking that stuff out.
Yeah, it was tight. There's no question about it. So actually, the SDSDA helped us with that, and we used low boy rail cars. And if you can get it down the shaft, it'll get across the level. Is kind of the way to think about things. And so we had to bring it in pieces that fit in the cage, and then we put it on rail cars. Well, actually, we would put them on the rail cars at the surface, roll it onto the cage, and then rolled it back there. It was certainly a challenge. And of course, the raised bore cutter itself had to go down to the 4850 level. For those that aren't familiar, you drill a 12-inch diameter hole from the top down, and then you put a reamer bit on. If you've ever seen a news story about a tunnel boring machine. It's kind of the same thing. And so the reamer is 12 feet in diameter, and it's got cutters on it that then rotate slowly, and that you pull that back up, and that way all the rock is falling down. Otherwise, you got to figure out how to get that rock up, and it's a lot harder to do it in that way. And so the cutter had to be brought down to the 4850 level, which means that we had to excavate actually a pilot tunnel to get down to the end of that, because that tunnel that the borehole connects to didn't exist before we started. And so that was part of the preparatory activities as well.
Remind people about the cage in the visitor center.
Oh yeah, that's a good point. So Jolie was just noting, so everybody probably went to the visitor center, excuse me, this morning before they came up to the Opera House. And inside of the visitor center is the cage that used to be in the Ross shaft. And so if you get into that cage, that is the exact same size as the current one. Current one's taller. There's more head space above you. And in fact, we're going to put a taller one yet in this winter. But the footprint doesn't change. That's all you got. The only way to make the footprint bigger is to excavate the shaft. And that's not something anybody was prepared to do.
Also at the visitor center today, they have a scale model of the cryostat steel erected that you can see. So the red beams that you can see behind them right now, you can see a scale model of it fully constructed, or maybe half constructed, in the visitor center today. If you get a chance.
Yeah, I'll just throw out also, Steve, that in the visitor center, they've got that model that shows all of the underground levels, and there is a 3D printed 2-scale LB&F DUNE caverns. And it's kind of hard to find, because despite how gigantic these caverns are, in the scale of the underground mine, they're not very big. And so you have to search for it a little bit, but you can get a good idea of the size compared to the overall mine.
Another question here.
Could you explain the word cryostat?
Uh-oh. Who wants to take what is a cryostat?
I think the cleanest and easiest explanation is a vessel that can hold very cold liquid. And so in this case, this technology has been leveraged from the natural gas industry. And so when I talked about 3-foot thick insulation, that's what's used in those liquid natural gas ships to keep that commodity at the temperature it needs to be. And so we're going to use that to keep the liquid argon at the temperature it needs to be, such that it can have those key interactions. The neutrinos can interact in that liquid argon. And so if I'm remembering correctly, -400 Fahrenheit? 300. Okay, so if you can distinguish that in your brain, congratulations. But that's what we're trying to accomplish in those cryostats. So the cryo is meant to imply cold, and essentially it's a very, very big cooler. It houses, as I said, the detector, as well as the liquid argon, which enables those beautiful interactions.
Another question here.
So you mentioned one of the important parts of DUNE being the fact that the beam is traveling through different medium, traveling through the ground. Is it simply the density of the medium, or does the type of matter affect that? And what is it about traveling through that different medium that actually affects the oscillations?
Is the question, what is it about matter?
The different medium that it's traveling through?
Mm-hmm. Yeah. A great question, because this gets at the core of the design of the DUNE experiment. When neutrinos travel through matter, the main difference is, they see more matter than anything else, for example, antimatter, and that enhances certain interactions that neutrinos have. We call it the forward weak scattering. I'm sorry, it's jargony, but that is all to say that, if when neutrinos travel through matter and some of those in the processes are enhanced, if the neutrino is normal ordering or inverted ordering, depending on which is the true answer, one of those effects are more enhanced. For example, you'll see more, we'll send muon neutrinos, predominantly muon neutrinos from Fermilab, and these muon neutrinos, as they travel in matter, the 800 miles, the type of flavor we're looking at the far detector is an electron neutrino. So in simple words, we're looking at muon neutrinos oscillating into electron neutrinos, and you'll see that what we call this is the electron neutrino appearance probability. You see that enhance if it's normal ordering, or vice versa. If it's inverted ordering, you see the anti-electron neutrino appearance enhance. So matter has that. When neutrinos oscillate through matter, they have that ability for us to be able to then get sensitive to these effects. In air, for example, this can't happen because the sort of potential that matter gives is not present.
Explain how many neutrinos out of the total number that we send here we actually detect.
Yeah, so Josh is suggesting I mention how many neutrinos we send from Fermilab end up here. This is an important question and something that went into our calculation of how many neutrinos we get in order to do these measurements. So the neutrino beam starts as a very pointed beam, and like any other beam, it does diffuse as it travels. In fact, by the time it gets to the far detector, it may be a few miles wide. So we start with millions of neutrinos at Fermilab at the near side, and over a course of three or 4 years, we'll see hundreds of those neutrinos. We'll see more, but then the specific measurements I was talking about, where you want to look at muon neutrinos that has oscillated to electron neutrinos, you end up seeing hundreds of them. It depends on what channel you're exactly looking at. You're looking at several hundreds versus several thousands, depending on you're looking for appearance of the new flavor, the electron flavor, or if you're looking for disappearance of the original flavor, which tend to be two different measurements.
Yes, ma'am. You mentioned a beam emanating from the northeast or eastern seaboard, wherever up there. It would emanate from there and come down to you here into your project. Would that be considered a line of sight beam, or would there be interruptions with that beam along the way, or how did they set that up to start out there?
About the neutrino beam, seeing any barriers?
I think maybe one of the points, if you can hear me, one of the points that may not be coming through quite is that the neutrinos go in a straight line, and they generally don't interact with anything. They'll go through the Earth as if it's not even there. They're like 1,000,000 times smaller than an electron, and so they just travel through molecules as if there's nothing there. It's like flying through space and missing moons, right? It's not, but some of them are going to hit those moons, and that's, along the way, there'll be some that hit the matter between us and Fermilab, and in the detector, that argon is nice and dense, and so that's how we get some to interact with the argon. But a lot of them, most of them, will pass through the detector, and we won't detect them either. But it is line of sight. It's a straight line. And so the beam actually goes downward at Fermilab at about 7 degrees, and it's coming upward at this end at about the same angle, because, of course, the Earth is round. And so then they come out, overpass spearfish, come out of the ground, and travel on into space. And you might worry about, well, am I being bombarded by neutrinos? And the answer is yes, you are right now. And it's not because of a beamline that's coming from Fermilab. Trillions of neutrinos are passing through you right now that come from stars, come from all kinds of different things. Bananas, even bananas. It's a YouTube channel. You can watch even bananas create neutrinos.
Well, excellent neutrinos 101, Josh. That's right. To put more of that into context, neutrinos are our messengers from the cosmos, right? I mentioned before, neutrinos from sun that's far, far away just come straight through to Earth, and we see one of the biggest flux number of neutrinos we see on Earth is coming from sun. Everything emits neutrinos, like Josh said, bananas, avocados. You also have smaller things emitting neutrinos like nucleus. Yeah, there is nothing in that beamline, nothing can stop them. So they'll come straight to our detectors.
So the diffusion of the neutrino beam, is that simply because of the limited focusing of the beam, or are there other effects at play?
The beam widening, yeah, it's just any beam, as you pass through, right, there is some level of divergence that happens, and we start with as focused of a beam as we can at Fermilab, but that divergence is inevitable in some sense. I guess for the NOAA experiment, which is also hundreds of kilometers away, I think the beam diverges, if I'm remembering right, about a mile or two by the time it gets to that detector.
The questions? Looks like the questions have all been satisfactorily answered. Okay, one last chance.
I was going to say, for all the answers, we won the bison, but we'll wait for the last question.
Good morning. Thank you for your time. Good morning. Thank you for your time. I'll try and limit this to fewer questions. You're underground to isolate signals from neutrinos versus other background radiations, I take it?
Why are you underground?
Yeah, that's right. Excellent question. If we can, we want to build all our detectors underground. That's because of cosmics. So particles coming from, from all around the Earth, they can interact with the atmosphere of the Earth, and you have many other particles produced. Cosmic rays is primarily the reason why DUNE is deep underground. You see about 1 million times less background when you go to 1.5 kilometers compared to what you would see on the surface. That's the primary reason. And it helps greatly. It helps take out one of the dominant backgrounds we would otherwise see on the surface by going this deep underground.
A follow-up question? Okay, that better. Follow-up question. So there are a lot of background neutrinos that aren't getting filtered by atmosphere or Earth. Can your detectors determine directionality of where they're coming from? How do you know that you're detecting the Fermilab source versus sources?
Yeah, great question. So the beam from Fermilab, it comes in a certain direction, right? If you think about any remaining cosmic rays, they tend to be isotropic. Of course, at a mile underground, you probably filter out many of the low to medium energy because of the density of the Earth. You do get some of them. With the atmospheric neutrinos, some of them does get into the detector. Again, the energy range of those atmospheric neutrinos and the spread in terms of angle of those neutrinos would be different. But what's really problematic is during the neutrino beam spill, when the neutrino beam is coming, we tend to we use what we call the triggering mechanism to try to select events that are happening during that neutrino beam is coming. And sometimes you can't completely avoid neutrinos that may be coming from the high energy cosmic rays or the atmospherics. So this is where our offline algorithms come in. So whatever inevitable background that we tend to see, we'll use our offline algorithms to try to look at many things, their directionality, their energy, what sort of signatures they're leaving in the detector, and try to filter them out. So it's an iterative process. The other thing to also keep in mind, to your question about background, the beam we get from Fermilab is not 100% muon neutrinos. So there is some contamination of electron neutrinos and tau neutrinos, which also come and, they have interactions nearby the detector or in the detector. And we'd have to also beam-based backgrounds also we would have to filter out. But this is something we do in all neutrino experiments, and there are many handles we have in order to tackle them. And one of the recent tools I'll mention, because Genesis is a term that, especially in the United States, with the machine learning trending a lot more, we do use machine learning in particle physics experiments. Typically, when you have big data, machine learning is a great tool, especially for DUNE, which is a liquid argon detector. The output of the detector, it's is this beautiful photographic-like images. So it's an imaging detector. So pattern recognition comes into play. So we also use that as a handle when we are tackling backgrounds or trying to find signals in a more precise way.
Okay, thank you, everyone. If you can give a round of applause to our underground scientists, that would be greatly appreciated. And thank you, Jarrett and Steve, for moderating today. We've got about 2 minutes to set up for the next group, which is called Setup, but with a C. And so just hang in there. We're going to get that set up, and the scientists will be here to answer your questions as well.
We'll just say thank you. Excellent questions. And I speak that on behalf of both Jolie and Josh. Really enjoyed it. Thank you.
Thank you.
Bye, everybody.